So you'll have a test on Monday, right? If you're in Dell's class, you'll have a test on Monday. And I think he posted something, I forget what the title of it was on Canvas, but some sort of file about being, what was it called? He posted something about, there's some sort of practice exam. So we can certainly go through that. It might be worth going through. And then I feel like we should talk more about limits. So that's kind of my plan for today. Certainly we can adjust that if need be. But let's go through this first, just so you can kind of get an idea of what his exam looks like, or his practice exam, or whatever he called. I think he called this the template in the files. Also, I was looking in his files, and there appears to be some sort of other practice exam that wasn't accessible yet. So hopefully that'll get posted or made available soon. Let's take a quick look. Something important to remember when you're taking an exam, read the questions slowly. Make sure you understand what you're being asked before you just jump right in. You don't want to do too much work, and you want to make sure you're answering the question being asked. So make sure we read these questions. So this one says, find the domain of the function f and express it in interval notation. So I see a few things going on here. I see all the things actually that I look for when I'm asking about domain. I see a logarithm, I see a square root, and I see a denominator. So let's just deal with them piece by piece. For the logarithm, we know that the insides of a logarithm have to be strictly greater than 0. So we know that x has to be greater than -3. For the square root part, we know that the insides of a square root have to be greater than or equal to 0. So we need 6 to be bigger than or equal to x. Or if you prefer to write the x on the left side, x is less than or equal to 6. Finally, we need to make sure the denominator is never equal to 0. So we're going to set 1 minus the square root of 6 minus x equal to 0 and solve for x. You might just be able to guess that x is equal to 5. It's going to solve that because 6 minus 5 is 1, square root of 1 is 1, and 1 minus 1 is 0. Or you can solve it by saying 1 equals the square root of 6 minus x, and then squaring both sides to get 1 equal to 6 minus x. So x is going to equal positive 5. And we want to exclude that. So we want x to not equal 5. And to me, the easiest way to actually write this in interval notation is to draw it on the number line. So let's draw on the number line what we want, and then we will write that in the interval notation. Let's see. The important points here are -3, 6, and 5. I don't need any other points. Specifically, I should not put 0 on there unless I actually need it. Okay. So let's see. I want to be less than or equal to 6 and bigger than -3 and not equal to 5. So I want everything from -3 to the right. I want to be bigger than -3. I don't want 5. And I want to continue all the way up until being less than or equal to 6. So I don't want any numbers bigger than 6. 7 would be a problem. I don't want any numbers more negative than -3. -4 would be a problem. So my domain here is looking like parentheses -3 to 5 parentheses union 5 parentheses to 6 bracket. Okay. Continuing on. So this next question does bring up something we probably need to, we're going to skip this next question for a second, come back to it. So moving on from number 2 to number 3. Assume that the weight W of a goat in Yellowstone National Park is given by the growth model. Use a little more space there. W of t equal to 420 t cubed over 64 plus 6t cubed for t greater than 0, or W of t is in kilograms and time t is measured in years. Find the goat's weight at t equal to 2. So all we're being asked to do here really is to plug in 2 for t. So W of 2 is equal to 420 times 2 cubed over 64 plus 6 times 2 cubed. And if I didn't think I was going to have enough time on this test, I might just stop and leave that there and then continue on to other problems. Right, that's a correct answer. I should probably simplify it, to be honest, but simplification is not the more important part. So if you feel like you're going to be The word I'm looking for on it. If you feel like you're going to be pressed for time, leave the simplifying until the end. We could simplify this. It's going to be 420 times 8 divided by, let's see, 2 to the third is 8. 8 times 6 is 48. 48 plus 64 is 112. I don't love all that. We can cancel a 2 here and a 2 here. 112 divided by 2 is 56. We can cancel another 2 here and another 2 here. That's 28. We cancel another 2 here and a 2 here. That's 14. We get 420 over 14. 42 divided by 14 is 3. So we get 30. 30 watts. I can't imagine he wouldn't want you to write the units there. To write the units. Yeah.
How simplified do the professors want the answer?
As much as possible.
Okay, so like if you put it the way that you had it at first, you probably lose some points.
Potentially. It's really, again, I don't know exactly, but yes, I'm sure he picked the value of 2 there because it is very simplifiable. Yeah. Find when does the goat reach a weight of 60 kilograms? Okay, so we want to know when the weight, what time it is when the weight is equal to 60. That might not be written in the most concise way, but the question is still, I think, relatively clear. We want to know how long does it take until the goat gets to 60 kilograms. So now we're not plugging into for time, we're setting the weight equal to 60 and solving for time. So we have 420t cubed over 64 plus 6t cubed. I would multiply both sides by the denominator and get 60 times 64 plus 6t cubed equal to 420t cubed. There's not a lot of space here, I gotta say. I would feel like I should have gotten more space, but that's fine. Distribute the 60, but let's be smart about it. I'm just gonna write 60 times 64 because I don't know what that is off the top of my head and I'm not too worried about it. Plus, things are probably gonna cancel out later when I divide. 60 times 6, though, I'm better at. That's 360 t cubed equal to 420 t cubed. Subtract 360 t cubed from both sides. 420 minus 60 is 60. Oh, that's going to work out well in my favor. 60 times 64 equals 60 t cubed. Divide both sides by 60. See, it would benefit us not to multiply the 60 times 64 here. So divide both sides by 60, you get 64 equal to t cubed. Take the cube root of both sides, you get t equal to 4 years. Sometimes it's really in your interest to not simplify right away. It's going to be better off if you don't. I don't know what that yes in the chat is for, but you have more to say. What do you say? Find what weight can, wow, that's the phrasing there. What weight can we expect for the goat to reach as t goes on and on and on? I cannot. I really need to get through this because there's a lot to say today. So I'm going to keep going at this pace. Yes. Definitely. So they're spelling it out for us here. They're saying take the limit as t goes to infinity. So we're going to take the limit as t goes to infinity of 420t cubed divided by 64 plus 6t cubed. I think we talked about taking limits to infinity last time. And one of the methods for taking a limit to infinity, especially for a rational function like this, is to divide each thing in the numerator and the denominator by the highest power of your variable that is in the denominator. In this case, they're the same. So we just divide everything by t cubed. Dividing everything by t cubed. We get 420. I would probably just do the simplification in my head here. I don't need to really write 420 t cubed over t cubed. I'm going to say 420 over 64 over t cubed plus 6. As t goes to infinity, 64 divided by t cubed gets very, very small. And then I'm left with 420 divided by 6. 42 divided by 6 is 7, so 420 divided by 6 is 70. The big goat. Maybe not, I don't know. Maybe what kind of goats these are. Maybe they get that big. That's well, like 150 pounds about, a little bit more. Question.
Right now, going through solving the limits, do we have to put like limit to t every time?
Yes, yes, you do. So you should be writing the limit as t approaches infinity as long as there are still t's in your expression. So actually, I want to be super clear about this. You write the limit here because there's still t's. You write the limit here because there's still a t. And then the next step, I no longer wrote the limit because there's no longer any t's. I said what t did, and then I found the value. So once you don't have your variable anymore, you no longer should be writing the limit. All right, let's look at the next page of this thing. We'll come back to number 2, I promise. I feel like we haven't talked about the difference quotient at all, but here's an example of it. So luckily, kind of, they're telling us what they want us to do, right? You could not have ever heard the phrase difference quotient and still know how to do this problem, or at least figure out how to do this problem. So we're being asked to find and simplify the expression f of x plus h minus f of x all divided by h. Here's what should happen in a problem like this. When we write it out, everything that's in the numerator that doesn't have an h should cancel. And then every remaining term that has an h, we can then factor out an h and cancel the one lone h in the denominator. That is almost always our goal with an expression like f of x plus h minus f of x over h, is to eventually make sure that that one h in the denominator gets canceled out. There might be other h's left over, but that one h in the denominator that's originally there, that one should get canceled. So I kind of like to write out what things are to the side. I know that f of x is 3x squared minus 5. So I know that f of something else is 3 times something else squared minus 5. In this case, the something else is x plus h. So I'm just going to write out my expression. My f of x plus h minus f of x divided by h is going to be, well, there's f of x plus h. It's 3 times x plus h squared minus 5. Minus, I'm about to make a mistake, 3x squared minus 5, all divided by h. I made a mistake. What did I forget to do? Yeah, I forgot the parentheses. And notably here, if I don't have the parentheses here, you're going to have minus 5, which is minus 10. Right, minus 5, subtract more 5 from it, you're going to get minus 10. But as I just said before, the things that don't have h's should cancel out. So if you see that you're getting like a minus 10 in the numerator, like, oh, I probably forgot to distribute the minus sign. I totally did. There should be parentheses there. And then if I distribute the minus sign, I can do 2 things at once here. I'm going to multiply out x plus h squared. That's going to be 3 times x squared plus 2xh plus h squared minus 5. And then I'm going to distribute the minus sign here and get negative 3x squared plus 5. You should write the divided by h each time. The minus 5 plus 5 adds to 0. I can't cancel the 3x squareds yet because I have to distribute the 3 first. That's going to be 3x squared plus 6xh plus 3h squared minus 3x squared, all divided by h. Now the 3x squared minus 3x squared is 0. The remaining terms in the numerator have an h, so I'm going to factor out an h from them. And be left with 6x plus 3h to the first, all divided by h. The h divided by h is 1. And then I'm left with 1 times 6x plus 3h, or just 6x plus 3h. And then, as we'll see in the near future, this is very intimately related to the limit definition of the derivative. We're just not there yet. But if you're thinking about like how the derivative of this function will be 6x, that's how we're getting there. All right, let's look at the next one. You're always welcome to ask questions. So many words. So again, it really is important to read these carefully. I'm going to say it again and again and again. Reading these questions carefully is going to save you time. As Jen likes to say, go slow so you can go fast. Read the question slowly, make sure you understand it so then you can do the appropriate work. A bacterial culture with n not equal to 40 triples every 20 minutes. N not being 40 means the initial population is 40, right? The population at time 0. Produce a table, okay, and give population for t equals 0, t equals 1, which is 20 minutes. I don't love that notation, but I'm not the one writing the problems. T equals 240 minutes and t equals 360 minutes. And give you a formula for nt in terms of t and n naught. Okay, so let's make our little table here. So we have t and n naught. And I'm going to write what t is equal to, but I'm also going to write the number of minutes on the side. So if t equals 0 is just 0. But then t equals 1 is 20 minutes. T equals 2 is 40 minutes. t equals 3 is 60 minutes. And then we know that at time 0, we're going to have 40 bacteria. And then every 1 unit of time, aka every 20 minutes, the population is said to triple. So that's not too terrible. 40 times 3, well, 4 times 3 is 12, so 40 times 3 is 120. And then in the next 20 minutes, it's going to triple again. And 120 times 3 is 360. And then the last one's kind of terrible, but not that terrible. It's going to triple again. I know that 3 times 300 is 900, and then 3 times 60 is 180, and 900 plus 180 is 1080. And I should have written, sorry, this is inappropriate notation up here. That should not be n naught, that should be n sub t. Apologies. And then we want to find a formula for n sub t in terms of t and n naught. Yeah, I don't love that. But we'll do it. So there's 2 different ways to do this. I'm going to try and do it the way I think that your professor probably wants you to do it, and then I can talk about the other way. So specifically, when you have an exponential growth or decay situation like this is growth specifically, but it doesn't matter if it's growth or decay, and you were told the multiplying by whatever time, told the doubling time, or the tripling time, or the quadrupling time, or the sum multiplying by a nice integer number time. There is a relatively easy way to come up with the formula for exponential growth. And here's what it is. The formula, n sub t, or I would probably write n of t, but fine. N sub t is equal to the initial population times the multiplication factor. In this case, it's tripling, right? It's tripling? Yeah. So times the multiplication factor raised to the t divided by how long it takes to do the thing. So right there is how long it takes to triple or multiply whatever the factor is. In this case, it would be 1, right? I'm not using minutes. I'm using units of time, which they specifically said each 20-minute period was 1 unit of time, which I don't like, but it's what's happening here. Nope, I'm wrong, because I read the question again, and I see that it says find the doubling time in minutes for this population. Find the double, oh, wow. Okay, sorry, my brain is not all the way. Oh, we can. I don't love these. It's challenging when they try to make the units weird, right? So they've said, okay. So I would point out that if, and actually I do like to say this, so I'm going to write this again. I've got n of t equal to n naught, which is 40, times 3 to the tth power. And I just want you all to see that at least according to my values for t and for nt here, this works. If t is equal to 0, 3 to the 0 is 1, 40 times 1 is 40. If t is equal to 1, 3 to the 1 is 3, 40 times 3 is 120. If t is equal to 2, 3 squared is 9, 9 times 40 is 360. So this is the right model here, but I could probably fix my t because this isn't measured in minutes, right? This is measured in units of 20 minutes, which again is terrible. So the way I'm going to fix this is not measured in t minutes. So the way I'm going to fix it, I'm going to use capital T, I guess, just to make life, just to have some differentiation there. I'm going to say that n of capital T is 40 times 3 to the, okay, what I should have up here is t divided by how long it takes to do the thing, which is 20 in this case, right? It takes 20 minutes for the population to triple, so I'm going to get t divided by 20. And you can check, if you plug in these numbers, you're still going to get the exact same results. I guess I could say 0 as well up here. If you plug in 0, 0 over 20 is 0, 3 to the 0 is 1, 40 times 1 is 40. If you plug in 20 minutes, 20 over 20 is 1, 3 to the 1 is 3, 40 times 3 is 120. So it still works the same way. Really don't like the way this problem's set up. But That's our model. Haven't answered the question yet, though. But I will point out, this is measured in minutes. So capital T does represent minutes here, where lowercase t represents 20 minutes. Kind of stupid. Sorry, I'll stop complaining about it. So then they asked us to do what? Right, and they told us the tripling time. Really, really important here that you don't just multiply it by 2/3 or whatever, right? If the tripling time is 40 minutes, the doubling time isn't 2/3 of that. It is not linear. It is exponentially related. So we have to do this kind of thing. Well, that means we're asking if you started off with 40 bacteria, how long it takes until we get to how many? 80. So we're going to set n of t equal to 80, and we're going to try to figure out what time it took. So then we're going to say, great, 80, sorry, it should be my capital N of t. Sorry, my notation's a little bit wonky here. So 80 equals 40 times 3 to the t over 20. We can't multiply the 40 by the 3. We have to divide by 40. So we're going to get 2, right? 80 divided by 40 is equal to 3 to the t over 20. And then it looks like they probably want me to get a decimal approximation. So I'm going to look up here what I've got. And I'm going to notice that I have a lot of natural log approximations. So I'm going to take the natural log of both sides. You can take any log of both sides. I would usually pick natural log anyway. But log-based n is also often the choice. But here, since I'm being shown all these natural logs, I should pick natural log. So I'm going to have that the natural log of 2 is equal to the natural log of 3 to the t over 20. The reason we're doing that is so that we can bring the power down and we no longer have our variable in the exponent. Then we're going to say that the natural log of 2 is equal to t over 20 times the natural log of 3. Wow, they're really funny. So then I'm going to solve for t by multiplying both sides by 20 and getting 20 natural log of 2 divided by natural log of 3. That's what t is going to equal. And then I guess I'll use these decimal approximations to say, well, that's approximately 20 times the natural log of 2, which is 0.69, divided by the natural log of 3, which is 1.1. And then they even told me, well, I don't love this here. They should have written 1.1 there if they're trying to be a little bit more truthful about what's going on. But this is approximately 0.63. So it's approximately 20 times 0.63, which is 2 times 0.63 is 1.26, so 12.6. So 12.6. 12.6 what? Minutes. It should be less than how long it takes to triple. If it were me, I would have stopped here. I would say, great, it's 20 natural log of 2 over natural log of 3 minutes. And if I have time, I will come back at the end and try to do this silly decimal approximation thing. All right, he did say no calculators, right? Yeah, okay. No surprise. Let's look at the next thing, unless there's questions about that. Oh, there is. Okay. I should ask, is this the way this has been talked about in class? It's fine if it's not, yeah.
What's like the formula, like if you add like two equals that would be like
Right, okay, sure. So that is the other way of going about doing this. So let me just mention that briefly because this is the nice way of doing it if you were specifically told a multiplying by whatever factor. But I'll point out that we also could have done this by setting it up as, I'll just write over here. We could have instead said n of t is equal to n naught times e to the kt. We'd still use the same data points. We'd still use the fact that, and I'm going to just say that t is time here. I guess I'll use, yeah, t is time, n of t is the amount. We know at 0 we have 40. At 20 minutes later we have 120, and 20 minutes after that we have 360. So here the way you would do it is similar but slightly different. You would plug in t equal to 0 to get n not equal to 40. So then we have n of t equal to 40 e to the kt. And then we're going to plug in t equal to 20 and n of t equal to 120. to solve for k. So then we divide both sides by 40. We take the natural log of both sides. Natural log of e to the stuff is just the stuff. And then we solve for k. K is equal to the natural log of 3 divided by 20. So then you can write your nice, shiny, brand new model as n of t equal to your n naught, which is 40, times e to the natural log of 3 over 20 times t. Which might look a little bit different than what we just did, but is actually the same. So I'll point out that we could simplify this. You don't need to simplify this, but you could simplify this to see if it's the same as the other one by doing the following. You could rewrite this as 40 times, check this out, e to the, I'm going to write it as t over 20 times the natural log of 3, and then bring that t over 20 up as the power of 3 using my logarithm rules. That's 40 e to the natural log of 3 to the t over 20. And then e to the natural log of some stuff is just the stuff. Hey, look, that's the same thing I had over there. So not that you should do it this way, I just want you to be convinced that doing it either way is going to produce the same result. Your results might look a little different, this versus this, but they are the same function. Either way, you should do it either way, whichever way you like better. That's the real answer, is do it whichever way you like better. Which I know is not always the satisfying answer, like it'd be kind of nicer just to do it this way, but that's not really how it works. Usually it's like, well, there's a couple different ways you can do it, and as long as you're doing it right, do it the way that works.
Both work.
They both work. Right, for an exponential. So now I will say this version of it is specifically, in my opinion, better if you're not given like a tripling or a doubling or a quadrupling time. Like if I said at time equals 0, I have 40 bacteria, and then 30 minutes later I have 75 bacteria. Well, then doing it this way is, or this the other way is less good. So I would always prefer to do it this way because I think it's more generally applicable, but both technically do work in either case. It's just you don't have a doubling time in that case. I just mentioned you have a multiplying by 75/40th time, which is silly. Okay, let's move along. See what's on this next page. What surprises await us now? The Pacific halibut fishery has been modeled by the equation 6 times 9 to the 8th power over 6 plus 4e to the negative 0.72 t, where f of t is the biomass, which is the total mass of all the fishies, in kilograms at time t. Find the limit as t goes to infinity of e to the negative 0.72 t. Good question. I like that question. There's a couple ways you could do this. Well, I should say, there's a couple ways you can think about this. There's probably one best way to do it. So I want you all to imagine in your minds the graph of just e to the x for a second. Think about what that looks like. If you're not sure, look at your right hand. Remember how I talked about how it's on your right hand, e to the x? I did talk about that, right? No. If so, again, my hand's not the best because I'm old, but if you look here, that line there, which looks much more well-defined on most of your hands, that looks like you, but make sure you're looking at your palm straight up. Don't look at it to the side. Look at it straight up like that. There should be like an e to the x there and like a natural log of x there. So what I want you to see is that e to the x goes up from left to right, right? And what I would specifically say here is that, is that if I was looking at e to the x, it looks like this. So very quickly, let me ask all of you, what's the limit as x goes to infinity of e to the x? Infinity, right? You go to the right, it gets real big. What's the limit, bless you, as x goes to negative infinity of e to the x? 0, right? As you go to the left, you get closer and closer and closer and closer to the horizontal asymptote y equal to 0. What if you change the sign of x? Well, if I graph e to the negative x, that flips it horizontally across the y-axis. So here's my best approximation of e to the negative x. That's pretty good, James. Sorry, I always have trouble graphing e to the negative x. So just graphically, we can see that the limit as x goes to infinity of e to the negative x, well, if I go way to the right here, I should be getting closer to And just for completion's sake, the limit as x goes to negative infinity of e to the negative x should be infinity. Because if you go to the left, it gets really, really big. Okay. So the thing to take away from this mostly for this particular problem is that as x goes to infinity, e to the negative x goes to 0. Now, that's not the way I wouldn't draw a graph to show this though, even though, at least not for the test. I would know that the graph was under my head, be like, okay, I know it's going to be 0, but here's what I'm really going to do on an exam. I'm going to write this in a way that's easier for someone else to understand what I'm doing. I'm going to write this as the limit as t goes to infinity of 1 over e to the positive 0.72t. You don't really need the positive sign there. I'm just trying to be very specific. Because we just all said, and I think it's easier for everyone to justify, at least it's easier for me to justify, that e to a very, very positive thing is really, really big. So 1 over something really, really big is very, very small. That's going to be 1 over infinity, which is 0. And that's the limit, just like we said it was. Okay, part B, and this is a smart way of asking this question, I think, because what they really wanted to ask you was the limit of the entire function. But they first made you think about what that one piece of it was doing, because that's kind of the harder piece. So put it here. So now I'm being asked for part B to find the limit as t goes to infinity of f of t. So it's the limit as t goes to infinity of 6 times 9 to the 8th over 6 plus 4e to the negative 0.72t. And we already know what happens to this part here. The limit of that is just 0. Everything else is a constant. So it's just going to stay as it is, right? T doing whatever it's doing doesn't affect what 6 times 9 to the 8th is. It's still 6 times 9 to the 8th. So we're going to get 6 times 9 to the 8th divided by 6 plus 0. 6 plus 0 is 6. 6 divided by 6 is 1. So we get just 9 to the 8th power. Okay. Question, sorry, go ahead. Yes, I would not, that's too big a number for us to calculate. If it was 5 to the third, I'd say write 125. But if it's getting bigger than like 1,000 after you would simplify it, which is very much is bigger than 1,000, you should not simplify. You should leave it as thing to a power. I know it's kind of, there's not a real like strict like this thing is small enough to simplify, this thing isn't. It's just kind of a judgment call. It's usually fine to leave something as something to a power, typically. I don't know the exact cutoff for when you should do something. Oh, no, there's a question over here too, yeah. No backward. Well, so what I thought when I was looking at Nadell's website, I found this as like a template for the exam. So that's why I printed it out and was showing it to you all, because I think this is what your exam is going to look like. Not 100% sure. I don't know because I can't read his mind. He didn't write anything, but that's what I was searching around for on his website, was just things that looked like they could be practice exams. So let's look at this next one. Graph y equal to 1 over 100 x cubed in a log plot. Okay. We know without doing any work that this graph should look like what kind of thing? A straight line, right? That's all you're ever going to have to do when it's log or semi-log. Is the function you're given is going to be either linear on a semi-log if it was exponential, or linear on a log if it was a power function. And this one is a power function because it is x to a power. We still have to do the work to figure out what the things are, but it's not going to be that terrible. So let's read the instructions so we do exactly what we're asked to. Clearly label your graph in terms of lowercase x, lowercase y, capital X equal to log base 10 of lowercase x, and capital Y equal to log base 10 of lowercase y. So here's where I'm going to start. By taking the log of both sides. I'm going to take my equation, y equal to 1 over 100 x cubed. I would probably just write it as x cubed over 100, to be honest. I don't need that 1 there. 1 times x cubed is x cubed. And then I take the log base 10 of both sides. I don't need to write the base 10 because it's implied. We're going to start rewriting things. Log of lowercase y is capital Y. Trying to make sure your capital looks very different than your lowercase. And I'm going to break up the right-hand side using my log rules. This is going to be log of x cubed minus log of 100. I'm going to use the power rule and say that capital Y is equal to 3 times log of x. And everyone show me on your fingers, what does log of 100 equal to? Less than that. This many. Because you're asking 10 to what power is equal to 100, not 10 times what number is equal to 100. So log of 100 is equal to 2 because 10 to the second power is equal to 100. It is nice in this problem that all the numbers are turning out very nicely, right? You don't have things you have to use calculators for. And then lastly, we're going to replace the log of x with a capital X. So we're going to rewrite this as capital Y equal to 3 times capital X minus 2. I usually try to make my x's look like a little curvy and my capital X's to look very straight. Maybe I'll put little serifs on them like that to make sure they're really like capital. That's a line that's not too hard to draw, right? It's got a slope of 3. It's got a y-intercept of -2. We can draw it. Whoops. Can we draw it? So I'm going to go down to... Let's see. So my y-intercept is -2. My slope is +3. So I'm going over 1 and up 3. I don't love how steep this graph is, but I don't have a choice. It'll look vaguely like this. If I had a straight edge, I mean, I guess I do have a straight edge. I would use it, but yeah. We do need to label the axes. So the horizontal axis here is the capital X equal to log base 10 of lowercase x axis. And the vertical axis is the capital Y equal to log base 10 of the lowercase y axis. Yeah, I think that's the whole thing. I can see asking a question like this, right? This doesn't seem too terrible if you know what to do. And really the first step here is if you're given some graph and then they want it in a log plot, the thing you have to do is take the log of both sides. If they wanted a semi-log plot, what would we do? Still take the log of both sides. Whether they want it as log, or semi-log, the first step is still to take the log of both sides. It's just that for semi-log, you're not going to end up with a log of x at the end of the day. You're going to end up with x being outside of the logarithm because, sorry, paper's there. All right. If you were doing semi-log, I'm going to try and make up something real quick here that's not so bad. If I said the same sort of thing, but I wanted y equal to, sure, 1,000 times, I'm trying to make the numbers real pretty here, so please don't judge my lack of originality. If my function was, 1,000 times 100 to the x, and I want that on a semi-log, I'm still going to take the log of both sides. That's always the first step to get it to be linear, whatever you're starting with. We just know that here it's going to be linear on a semi-log because it's starting with an exponential function. So then if I took the log of both sides, again, you can't multiply those together. You have to keep the 100 and 1,000 separate from each other. I've got log of y equal to log of 1,000 times 100 to the x. We break it apart. Log of y becomes capital Y. We have log of 1,000 plus log of 100 to the x. We have capital Y equal to log base 10 of 1,000 is how many? And before we can take the log base 10 here, we bring the x down in front using the power over logarithms. That's going to be plus x times log of 100. And then we simplify this because we can. And that's a lowercase x still, right? It didn't magically become uppercase. That is a capital Y equal to a 3 plus 2 times x. Lowercase x. So my semi-log graph here, the horizontal axis is regular old X. The vertical axis is capital Y equal to log of regular Y. And then we would graph Y equal to 3 plus 2X. So my y-intercept would be positive 3. My slope would be positive 2. And it's going to look vaguely like that. So the process for finding the equation is pretty much the same either way. You take the log of both sides, simplify until you get capital Y equal to either some m lowercase x plus b, or for log, some m uppercase x plus b. Either way, yeah.
Can you re-explain how you got the lowercase x again and the
Sure. So from this step to this step, I use the powerful logarithms, which says if you have log of something raised to a power, you can bring that power down in front of the logarithm. So that's why when you have an exponential thing and x is in the exponent, it never ends up staying in the logarithm. It always comes down in front of the logarithm, which is why it's not log, it's semi-log. Cool. So many things. I like this question. I think this is a good question. I hope he asks you one like this. I think it's very straightforward and doable. Limits. Okay. And then the other one was a limit too. Sure. So let's, before we tackle this limits page and the previous limits page, let's talk about limits for a bit. That's kind of the other thing I want to talk about today. So limits. Which we haven't really talked about at all in this class yet. Right? At least not in this co-class. Did you talk about limits in class yesterday? A little bit. It's kind of talking about all the things. Like there's so many things to say about limits. So that's a lie. We totally talked about limits on Tuesday. We talked about limits to infinity. Now we need to talk about other kinds of limits, meaning limits that are not necessarily to infinity. So let's see, I'll start here. Yeah, let's start here. Sure. So let's look at this function. We're going to graph a piecewise function. Piecewise functions are often used when kind of trying to see what is happening with one. So I've got f of x equal to x squared plus 1 when x is less than or equal to 0. I have x plus 1 when x is greater than 0 and less than 3. And the square root of x plus 1 when x is bigger than or equal to 3. I'm going to graph this. That looks kind of blurry. Okay, better. So graphing this piecewise function, I'm going to focus first on, well, x squared plus 1 is a parabola shifted up by 1, and that's going to be as long as x is less than or equal to 0, or left of x equal to 0, or left of the y-axis. So when x is 0, y would be 1, and it's going to be this parabola that looks vaguely like this. 0.01 there. Moving to the middle piece here, where x is between 0 and 3. I know that it's a straight line, right? It's y equals x plus 1. And when if x could be 0, I would get y equal to 1. So fortunately, I already have that point there. So they're going to meet up perfectly. And then if x could be 3, I would get y equal to 3 plus 1, which is 4. And I don't quite get that. I have an open circle at 3, 4. And then to the right of 3, actually at 3 and to the right of 3, if x is bigger than or equal to 3, y is equal to the square root of x plus 1. That looks like your usual square root function. And if we plug in 3, 3 plus 1 is 4, the square root of 4 is 2. So I get that point right there. And then it kind of looks like your usual square root function, just kind of going off like that. So there's my piecewise function. Not that we've defined it yet, but it is notably discontinuous. Right? It's not continuous everywhere. You can see just by the way I had to draw it. I had to lift my pen off the paper. Let's talk about some limits. So, question A here. Yeah, let's write it that way. What value does y get closer to or approach? Approach, I can spell. Yes, I can. As x approaches 0 from the left-hand side or the left side. That's a lot of words to write. I don't want to write all those words. Here's the way we generally deal with this. We write this as the limit as x approaches 0 from the left side or the less than side of 0 of f of x. Well, let's look at the picture. As x is getting closer and closer to 0 from the left-hand side, what are the y values getting closer and closer to? Yep, positive 1. That's it. That's what the limit is in this case. As x approaches 0 from the right, the y values get closer to positive 1. How about from the other side? Well, what about the right side of 0? Well, if x approaches 0 from the right-hand side, the y values also approach positive 1. So we can say that the limit as x approaches 0 from the right of f of x is also equal to 1. And, important fact, when the left-hand limit and the right-hand limit are the same, we say that the overall limit or the double-sided limit is also equal to that value. So we can say that since the limit as x approaches 0 from the left of f of x is equal to 1, and the limit as x approaches 0 from the right of f of x is equal to 1, then we can conclude that the overall double-sided limit as x approaches 0 of f of x is equal to 1. And all that means is that as x gets really, really close to 0, the y values get really, really close to 1. What it doesn't mean is that we know anything about what's going on at 0. This function, I could have changed it up a little bit and made that point an open circle there and put the point up there like 0, 4, and the limit would still be 1. Because the limit, and I'm gonna say this like 1,000 times, the limit as x approaches 0 does not actually care what happens at x equal to 0. It cares about what happens on either side of 0, super duper close to 0, but not actually getting to 0. We don't care what happens at 0. We care what happens immediately to the left and immediately to the right. We'll see that more in a minute. Let's continue though. The other place I'm intrigued about the limit here is what's happening at 3. So what about the limit as x approaches 3 from the right-hand side of this function? Well, again, let's take a look. Here's 3. As x is coming at 3 from the right, the y values are getting closer and closer to what y value? And I didn't label that point, so that point's 3, 2 there. Yeah, the y values are getting closer and closer to positive 2. So the limit as x approaches 3 from the right of f of x is equal to positive 2. And you already know what I'm going to ask next. What about what happens as x approaches 3 from the left-hand side? Yeah, so as we approach 3 from the left, the y values are getting closer and closer and closer and closer to 4. Do they ever actually equal 4? No. Do we care? Also no. Doesn't matter that we don't actually get to 4. It just matters that we get super close to 4, right? If x was 2.1009s and you added 1 to it, you'd get 3.1009s, which is very, very close to 4. So that's all we're concerned with here is closeness. Oh yeah, as x gets closer and closer to 3, the function gets closer and closer to 4. We do say that the limit is equal to 4. That doesn't mean the function equals 4. It just means that what we're saying with this, what this notation means is, and these are the words you should hear in your head when you see a limit, is as x gets close to 3 from the left-hand side, y gets close to 4. That's what that means. It doesn't mean anything about equaling 4 or x actually ever equaling 3. How much time? How much time? Okay, I still got 30 minutes. Yeah, sure. Oh, yeah. Sorry, one more thing to say here. So since the left-hand limit and the right-hand limit are approaching different values, that means the overall double-sided limit doesn't exist. So we would say that the limit as x approaches 3 of f of x does not exist. I would ask you to do me a favor, just because it annoys me. Don't write equals does not exist. Just say DNE, don't say equals DNE, or do, but don't let me see it because I think it's terrible. That's fine, yeah.
that point at 0 included and you put one.
Uh-huh.
Like, but you wouldn't move the line,
Uh-huh.
it's still there, right?
Yeah.
You would still just look at, as it's approaching.
Yes, let's talk about that for a second. So what if my function was the following? F of x is equal to the following terrible thing I'm about to make up. It's equal to x plus 4 when x is less than or equal, sorry, less than, not equal to, strictly less than 1. And it's equal to, sorry, I'm thinking about something else here. It's equal to, sorry, I'm trying to make up something that's gonna work. Just one moment, please. X squared, that's stupid, James, but it's fine. X squared plus 4 when x is greater than 1, and in the middle, it's gonna be 7 when x is equal to 1. So let's graph this thing. So from the left-hand side, it's just the straight line y equals x plus 4. Gonna look vaguely like this. Not my best work ever. When I plug in 1, I know 1 plus 4 is 5. And the right-hand side of that is going to look like the parabola x squared plus 4. So it's going to kind of look like this. And then at the point 1, we have defined this to be equal to 7. So there's the open circle 1, comma 5. There's the closed circle 1, comma 7. Let me zoom in a bit so you can see that better. And here's what I would say. The limit as x approaches 1 here exists. The limit as x approaches 1 from the left of f of x, well, again, as x gets closer and closer to 1 from the left side, what y values are the function getting closer and closer to? They're getting really close to this many, 5, right? Because if you plug in like 0.99999, you're going to get 4 plus 0.99999, which is 4.99999, which is really close to 5. So again, we're just asking, what is this function getting close to? Oh, the function is getting really, really, really close to 5. So we say the limit is 5. On the right-hand side, same deal. As x approaches 1 from the right, so if x was like 1.0000001, if you square that, it's even closer to 1, right? 1.0001 squared is like 1 point, lots of zeros, 1, excuse me. Plus 4 is 5 point, lots of zeros, 1. So it's really close to 5 again. And like I said before, if the left-hand limit and the right-hand limit are the same, that means the double-sided limit is also that. So this tells us that the limit as x approaches 1 of f of x is indeed equal to 5. And I'm going to remind you that I said a lot already, the limit doesn't care what's happening at the value x is approaching. I don't care that when x is equal to 1, I should say I don't care. The limit doesn't care that when x is equal to 1, y is equal to 7. Limit cares that when x is super duper close to 1, but not equal to 1, that the y values are super duper close to 5, but not necessarily equal to 5. Yeah.
Closed circle at like 1,7, and they asked us like f1.
It would not exist.
It's not.
Right. So here f of 1 is 7. Right. If I remove that point and then like took out that part right there, right, then the limit would still exist as x approaches 1. It would still be 5, but f of 1 would not exist because we haven't defined the function to be anything when x is equal to 1. Good questions. Okay. So that's the idea behind limits, is you're just asking, as x is close to something, what do the corresponding function values happen to get close to? And sometimes it's really easy to answer that question. Sometimes it's less easy to answer that question. Gosh, can I get back? Okay, so sure, I love all that. It's fine. So here's kind of the, yeah, we can skip this. So I'm trying to say the things so you can see the things. All right, so how do we deal with limits as x approaches a real number as opposed to infinity? Well, the usual first step is just to say, well, what if I did plug in x equal to whatever it's approaching? Like, for example, if I had the limit as x approaches 2 of x squared plus 3x plus 4. I could graph it. I'm not going to graph it. But if I graphed it, or if you graphed it, you know I'm gonna have what kind of graph? Parabola. And it's not gonna have any breaks or anything because it's a nice parabola. It's a polynomial. Polynomials are famously continuous everywhere, differentiable everywhere. So I know that either side of 2, the point in between them is going to be defined to be like the thing in between them. Right? I could do a very kind of terrible job of graphing it. I don't know. It's something like this. Who knows? The y-intercept's 4, I guess. Sure. It looks vaguely like that. Wow, that's the worst parabola I've ever drawn, probably. So, and then, but the point is there that as x approaches 2, the y values are going to approach whatever f of 2 happens to be. So the y values just get closer and closer to that value there from either side. Or to say it with many less words, when you have a limit as x approaches a number, try plugging in that number to your function and see if you get a real value. If you do, 99 times out of 100, that is what you're actually going to get as your limit. There are some exceptions to that, specifically for piecewise functions. If someone gives you a piecewise function, you cannot apply this rule. Typically, you have to do more exploration. But for regular looking functions, we have something called the evaluation theorem. Regular is, I know, not a very good term. I'll expand on that in a little bit. But for functions that look normal-ish, you can just plug in whatever x is approaching. So here we're going to plug in 2 and get 2 squared plus 3 times 2 plus 4 and get 4 plus 6 plus 4, which is 14. That's it. And that's kind of true for any sort of typical function, meaning any polynomial, any rational function on its domain, any trigonometric function on its domain, any exponential or logarithmic function on its domain. So regular functions, as long as they're defined at the point you're looking at, you can usually find the limit just by plugging in the value that x is approaching, which is great. Yeah.
So we just take it as like the domain of real.
You can typically just plug it in, as long as it's not some strange piecewise thing. Now there are there? No, I was thinking so. So that said, well, actually, let me give you one more example here. Let's say we have the limit as x approaches, sure, 2 of x squared minus 4 over x squared minus 5x minus 6. So here's what you should not do yet. You should not start factoring this thing, even though it might be tempting to. You should just plug in 2 and see what happens. Plug in 2 and see what happens. All right, drum roll, please. In the numerator, we get 4 minus 4, which is 0. In the denominator, we get, do we get 0? 4 minus 10 is negative 6. Minus 6 is negative 12. We definitely do not get 0 in the denominator. What's 0 divided by not 0? 0. We're done. That's the answer. So the thing here, and people will often ask questions like this to try to maybe trick you a little bit, is that if you look at this and you're not being careful, you might factor it and say that the top factor is x minus 2 times x plus 2, and you might incorrectly factor the bottom as like x minus 2 times x minus 3, or some other wrong way of factoring it. Because here the denominator would factor as x minus 6 times x plus 1. So don't get fooled into getting a 0 over 0 when you don't really have one. Always, we should plug in what x is approaching first just to see if it works. Yeah.
And then is the other option to divide all of it by x squared?
No, it is not. And I'm really glad you asked that. So the only time we can divide everything by the highest power of x in the denominator is when x is approaching what? Infinity or, right. Other than that, we don't apply that method. I'm glad you asked that. I wasn't thinking about that, but I see people do it all the time. So only divide by the highest power of x in the denominator if x is going to infinity or negative infinity. So typically what we encounter for a lot of limits is something like this. The limit as x approaches 2 of x squared minus 4 over x squared minus 5x plus 6. And now if you plug into sadness occurs, we get 4 minus 4 over 4 minus 10 plus 6, which is 0 over negative 6 plus 6 is 0. I want to disabuse you of any notions that 0 over 0 is equal to something silly like 0 or 1. Not. Well, actually, that's true. It's not always. It could end up equaling 0. It could end up equaling 1. It could end up equaling 5 or 17 or pi or infinity or negative infinity. It could be anything. So when you see a 0 over 0, just like last class when we saw infinity over infinity, that's what's called an indeterminate form, meaning it can literally take on any potential value. We have to find the one that it is. So this is where we're going to do some factoring and canceling. So we're going to look here. So when you see 0 over 0, what does 0 over 0 mean? Right, but what does it really mean? It means do more work. That's what it really means. Or at least that's what you should take it to mean, because that's what it means for you. If you get a 0 over 0 when you do a limit, you're like, oh, I got to do something else. That's not a final answer almost ever. I think ever, but it's never good to say ever. So here, we're going to rewrite this as the limit as x approaches 2. I'm going to factor the numerator, x minus 2 times x plus 2. I'm going to factor the denominator. I know that x minus 2 has to be one of the factors because I plugged in 2 and got 0. The fun fact, that's the fundamental theorem of algebra, is if you plug in a number to a polynomial and get 0, x minus that number had to have been a factor. So I know that x minus 2 is a factor, and then I know that the other factor is going to be x minus 3, because I need x times x to be x squared, and minus 2 times minus 3 to be positive 6.
I remember taking the derivative.
That is, I think what you're thinking about maybe is L'Hopital's rule, which is something that we are not allowed to use yet. We will eventually learn it in this class, probably. But yeah, for right now, you should pretend like, if you've never heard of L'Hopital's rule, great. If you have heard of L'Hopital's rule, pretend like you haven't. You definitely should not use it on this first exam. X to the highest power. So let's see what happens if we do that. But actually, let me finish this first, and then we'll do that. So here's what I want to point out. X is getting really close to 2. It's not equal to 2. Really important, it's not equal to 2. We don't care what happens at 2. So if X is like 2.00001, what's 2.0001 minus 2 times 2.000? You don't need to write this part down, but you can. Sorry, I should say the words. 2.001 minus 2 times 2.001 plus 2 divided by 2.00001 minus 2 times 2.0001 minus 3. So the thing I really want you to focus on here is, what's this part divided by that part going to be? 1, because they're the same. So as long as x isn't 2, this part divided by this part is always going to be 1, because they're always going to be the same. That's why we can say that, as far as we're concerned, this limit is the same as the limit as x approaches 2 if we cancel those pieces. Because as long as x isn't 2, which it never is if we're approaching 2, then x minus 2 divided by x minus 2 is always going to be 1. Now, if x was 2, it would be a problem, because then you have 0 divided by 0, which is a big problem. But the whole idea here is that essentially you can factor and cancel the problematic piece and not change the value of the limit. So here we're going to get x plus 2 divided by x minus 3, and then we can plug in 2 and get 4 divided by negative 1, which is negative 4, which is what this was going to get really close to, right? This is going to be 4.0001 divided by 2.001 minus 3 is negative 0.9999. Almost 4 divided by almost negative 1 is almost negative 4. So it makes sense that the limit's going to be negative 4. So this is how we deal with a limit that's a 0 over 0 type, is we typically, what I like to say is do some algebra, factor and cancel, or maybe multiply by a conjugate and then factor and cancel, or maybe get the common denominator and then factor and cancel. So let's look at one more. Oh, question. Yes, as long as it looks like you can factor it. So let me show you one more example, because I want to show you a thing. Let's say we had, in fact, why don't you all try doing this one? The limit as x approaches, do I like that one? Sure. X approaches 9 of x squared minus 10x plus 9 divided by x minus 9. If you check plugging in 9, you should see that you do get 0 over 0. You should always check just to be sure before you start doing any work. Make sure you write the limit every time. So we have the limit as x approaches 9 of x minus 9 times x minus 1 over x minus 9. Cancel. I would still probably write one more step, although you could probably skip this step. I'm going to write the limit as x approaches 9 of x minus 1. Then I can plug in my 9 and get what? Right. And you could write 9 minus 1 if you really want to. You don't have to write the limit anymore, though, right? Because I don't have any x's here, so I should not write the limit. And that's going to be 8. One thing I would like you to see about this, just because I think it's nice to see the graph here. So if I was to graph this function, y equal to x squared minus 10x plus 9 over x minus 9, it simplifies as y equal to x minus 1, as long as x isn't equal to 9. Right? X can't be 9. If you plug in 9, what do you get? 0 over 0, indeterminate. So it's this function as long as x doesn't equal 9. Here's what it looks like. It looks like the nice old regular graph of y equals to x minus 1, which is a straight line, y intercept of 1. Looks kind of like this. And then over here at where x would have been 9, the y value would have been 8. And if someone was to ask you a question about like the domain and range for this function, we can say that the domain of this function is everything except for 9. So everything from negative infinity to 9, union 9 to infinity. And the range is everything except for, don't get 8. Kind of cool. All right. Not a lot of time. Let me show you 2 more examples. Oh, yeah, I gotta say 3 more things. Okay, so I did promise you we're gonna get back to that first question. So here's another example of a limit you might encounter. Limit as x approaches 4 of the square root of 2x plus 1 minus 3 over x squared minus 16. And it's good to mentally check, but I don't want to write it out. So I'm just gonna say, okay, if I plug in 4, the top is going to be the square root of 9 minus 3, which is 0. The bottom is going to be 16 minus 16, which is also 0. So it definitely is a 0 over 0 type, which means I have to do something. I know that plugging in 4 is a problem. I would really like then to be able to cancel a factor of x minus 4. Because x minus 4 is what's problematic. The bottom, that's going to be easy. I can factor x squared minus 16 as x minus 4 times x plus 4. In the top, that's not going to be so easy. That doesn't just factor without doing something else first. So before we can start factoring and canceling, we're going to have to multiply the top and bottom by the conjugate of the thing that has a square root. So the conjugate of the square root of 2x plus 1 minus 3 is the square root of 2x plus 1 plus 3. And you can't just multiply by anything you want. You have to multiply by 1. So the conjugate divided by the same conjugate. And the denominator is just still x squared minus 16. To multiply these conjugates together, well, we could FOIL it out, but the reason we're doing this, the reason we're multiplying this by this is that the middle terms are going to cancel. When you multiply this out, you still have a limit because there's still x's. Square root of 2x plus 1 times the square root of 2x plus 1 is 2x plus 1. I'll write the whole thing out. Square root of 2x plus 1 times 3 is 3 times the square root of 2x plus 1. Minus 3 times the square root of 2x plus 1 is minus 3 times the square root of 2x plus 1. And finally, minus 3 times 3 is minus 3 squared, or minus 9. And the denominator, I'm just going to leave as x squared minus 16 times the square root of 2x plus 1 plus 3. You always want to actually multiply out the things that are conjugates. And you always want to never multiply out the things that are not conjugates. And now look what happens. The positive 3 squared root of 2x plus 1 and the negative 3 squared root of 2x plus 1 add up to 0. Which will always happen when you multiply something by its conjugate. Is that you'll get the first thing squared minus the second thing squared, and the middle terms will add up to 0 every time. That's why we do it. Then we're going to get the limit as x approaches 4 of 2x plus 1 minus 9 over x squared minus 16 times this other garbage. And then we're going to simplify the top. That's 2x minus 8 on top. And then we're going to factor out the 2 on top, and we're going to get the limit as x approaches 4 of 2 times x minus 4 on top, and I'll factor the x squared minus 16 as x plus 4 times x minus 4 on the bottom, and then still times the square root of 2x plus 1 plus 3 in parentheses. And now I can finally cancel the thing that I said I wanted to cancel. I want those x minus 4s to cancel, because right now, if I still were to plug in x equal to 4, I would get 2 times 0 on top over 8 times 0 times something on the bottom, and I'd still have 0 over 0. But now, once I cancel those factors that are becoming 0 when I plug in 4, now I can say I have the limit as x approaches 4 of 2 over x plus 4 times the square root of 2x plus 1 plus 3. And now I can just substitute in 4 for every remaining x and get no limit anymore, 2 over 4 plus 4 times the square root of 9 plus 3, which is going to be 2 over 8 times 6, cancel a 2, and you get 1 over 24. Okay. There are lots of additional examples on handouts that Grant has posted on his website. I would encourage you to look at them. There's one other example I really do feel like I have to say something about in the last 7 minutes here. Yeah.
Are the handouts on the website?
Yeah, on Grant's website,
Oh,
which are linked from Canvas, right? If you look at our Canvas, Grant's website is, I think it's under like useful links, I think. So the last thing I want to talk about, yeah, no, it's going to work some of the time. So I would say whenever you have a limit that's a 0 over 0 type, you have to think about, well, can I just factor and cancel? Or is there a square root I need to multiply by a conjugate? Or is it something totally different, like the limit as x approaches 0 of sine of x over x? Typically, yeah. There are a couple other corner cases, but yeah, conjugates are usually only for square roots. So what happens here if we plug in 0? Well, we get sine of 0 divided by 0. And what's sine of 0? It's 0. So there's a couple ways to show what this limit is. I think the best way to show you is actually to graph it. So let's look at the graph real quick. Not view, come on. Because there is something super important about this that you should all get to see. So here's the graph. Y equal to sine of x. There's good old sine of x. And then if we divide it all by x, look at that. So specifically, it looks like it's defined everywhere, but if you zoom in enough, undefined, it's 0, which makes sense, right? Because it's 0 divided by 0. But you might notice that the y values are really, really close to what value? Right, 0.99999. Oh, we're getting really close to 1. So it shouldn't surprise us by looking at the graph that the limit as x approaches 0 of this function should be positive 1, both from the right-hand side and from the left-hand side. So that's how we're going to justify to ourselves right now that this limit is equal to 1. So what I would say here is that we're just going to take it on graphical evidence that the limit as x approaches 0 of sine of x over x is equal to 1. Now, really, I would like to say something more general. And that here is the case. Really, it's the limit as some stuff approaches 0 of sine of some stuff over the exact same stuff. If you have sine of stuff over stuff, and the stuff is approaching 0, then that limit's going to equal 1. So for example, here's kind of something that seems maybe a little suspect. The limit as x approaches pi over 2 of sine of x minus pi over 2 over x minus pi over 2. So let me ask you two questions. I could not solve this algebraically. This cannot be done algebraically. Sorry, someone was asking on the chat, how would you solve this algebraically? Cannot do it algebraically. You can do it using L'Hopital's rule later, but that's later, not now. So I have sine of some stuff over the exact same stuff. Check one. Is the stuff approaching zero? It is, right? It's not that the limit, it's not that x is approaching zero necessarily. It's that whatever you have inside is your stuff. It's that stuff is approaching zero. So this looks like sine of some stuff over the same stuff, and the stuff is going to zero. So this limit is going to equal 1. Okay. What if you have something a little bit different? And I know we're almost out of time here. What if you had something like the limit as x approaches 0 of sine of 9x over 2x? So, second question, is the stuff approaching 0? Well, x is going to 0. Is 9 times x going to 0? Yeah, if x is approaching 0, 9 times it is also approaching 0. 9 times 0 is still 0. Same for the denominator. 2 times 0 is still 0. So both the stuff inside the sine function and the denominator are both approaching 0. But here's the other question, which I know you already know the answer to. Are they the same? No, they are not. 9x and 2x are very different than each other. And the problem is you can take the 2x out and like bring it out as a factor as a 1/2 in front, but the 9 is stuck. You cannot get rid of that 9 inside the sine function. The sine function is protecting 9x from everything that might attack it. So what do? Well, we employ a method that I like to call the wish method. I wish I had sine of 9x divided by 9x. So I'm going to make it happen. I'm going to rewrite this as the limit as x approaches 0. And I'm going to write 2 fractions instead of 1. I'm going to give myself 2 fractions. And in my first fraction, I'm going to write the numerator. And in the second fraction, I'm going to write the denominator. I haven't changed anything yet. I've just written it in a very bizarre way, but nothing is different. So now I'm going to ask the question again. What do I wish I had beneath sine of 9x? Right. But if I divide by 9x, I better also multiply by 9x. Cool. So then we simplify. 9x divided by 2x, the x's can cancel, and I just have 9/2. So those x's get to cancel out to be 1. And I have the limit as x approaches 0 of sine of 9x divided by 9x times 9/2. Just to be completely explicit about my work here, when you have the limit of a constant times a function, you can put the constant out in front of the limit. That's one of the limit rules that we did not talk about today or ever, but you might have mentioned in class. But if you have a limit of a function times a constant, that constant can be brought out in front of the limit. So it's 9/2 times the limit as x approaches 0 of sine of some stuff over the same stuff. And since you have the limit as x goes to 0, and you have sine of something over the same something, and the something is also going to 0, that limit has to be 1. So this part here is equal to 1. So we end up getting 9/2 times 1, which is 9/2. So that's how you deal with something where the stuff inside the sine function and the stuff in the denominator are not quite the same. You wish for it to be true, and then you make it be true. And I would say more, but I'm out of time.